Okay guys, so welcome back again to another video. So we have talked about the carbocation formation in our previous video, and in this particular video we are going to talk about the rearrangements which can occur based on this carbocations. So I'm going to talk about mainly three rearrangements. So we call these rearrangements as Van Even rearrangements. So sorry about the pronunciation if I am mistaken. So the first one, this is the common thing we all know about this particular rearrangement, the hydride shift. Right? In the basic organic chemistry, we have talked about this. So let's say we have like this. We have hydrogen and hydrogen over here, and we have CH2CH3 over here, and another CH2CH3 over here. So when the carbocation or the positive charge in this place, this is relatively unstable, right? But if your positive charge is moved into this particular place, this particular carbon atom, then it's relatively stable. Why? Because there is an electron push from these two R groups, but there are no R groups on this particular carbon. So what happens is there is a hydrogen, right? There's a hydrogen. This hydrogen can shift to this place by breaking this bond and forming this new bond. So we can obtain our new structure. Now this is our positive charge, which is much more stable because the electron density the donation of electron density from these two R groups. So we call this particular rearrangement as hydride shift. Okay, great. So the next thing is the methyl shift. The same thing, like this, just the same thing with the methyl group. Let's say we have a R group over here and another R group over here, and we have a methyl group over here. So here we have a hydrogen, and a positive charge. And then you can see now the positive charge on this particular place is not stable, but in this particular place it's much more stable because of this electron density towards our carbocation center. Okay, now our methyl group can shift into this place, resulting our newly formed carbocation, which is like this. We call this as methyl shift. And then finally we are going to talk about 1,2 alkyl shift. So let me take an example for it, right? So here let's say we have a ring like this, okay, and we have this positive charge over here. Okay, now you can see this is our main ring, but this small ring on here, this ring, look at this. This is highly strained, right? If you remember about your organic classes, we have discussed the organic rings. There are 3 carbon centered ring, 4 centered ring, 5 and 6, right? We have identified these two as the most stable, like the less stellical hindrance, because the ring strain is there, right? There's a ring strain. In this case the ring strain is so much higher, but the less ring strain, right, the lowest ring strain contained with these two structures. There are other factors are also contributed, like the thermodynamic aspects, but let's do not go into that much details. Just for this case, you need to know that the ring strain is much more less when it comes to when the ring contains more carbon, right? Because when the carbon number is increasing, the bond angle between two carbons are increasing, so ring strength is reduced. So in this case, there's a positive charge over here. You can see if our bond can be formed between this carbon, the ring strength will be less. So we can use a shift based on this ring strength. So now this one will be formed on here. This would be our inner. This is the now both of these cases, right? The hydride shift and the methyl shift both are based on the stability of the carbocation, right? Like now this positive charge, where we can put this positive charge to get the effect of this particular positive charge reduced, right? I mean, if I put the positive charge in this place, it has a much more effect on the instability, right? But if I put the positive charge in this way, in this place, the effect of these two R groups will cancel this positive charge for some fraction. Same happens here, right? Because of the donation of electron density, this positive charge will be diminished if it's placed on this place. But in this case, that's not the factor we are talking about. We are talking about the ring strength. In this case, the molecule is much more unstable because of the ring strength. But if you can see here, there is a very good opportunity right here. You can see a very good opportunity to reduce the ring strength, because it can easily go and bond with this particular carbon because it is positive charge. So that's the case you need to understand in this particular case, right? So we call this one as 1,2 alkyl shift. Plus 1,2 place, right? 1,2 alkyl shift. So these are the main three types of rearrangements which we are commonly occurred on biosynthetic pathways, and there is a special thing. This is not a common thing, but some more complex molecules contain this kind of rearrangements, right? So this is not common. I need to understand this is not common. Let's say we have a molecule like this. We have a positive charge over here and we have a double bond over here. And now what happens is there is a possibility to rearrangement like this hydrogen to shift over here to orient as this, like, so this is possible, like, but if I give you a molecule like this one, right, and I say this one. So this is not possible. This is possible, but this is not possible. You must have an idea, like you must have some kind of answer why this is not possible but this is possible, right? It's because of this double bond, right? So when this shift happens, right, this is a 1,3 shift, right? You can see it's a longer shift. That's why I have told you this is not common. So if this can happen to your molecule, what happens is your positive charge now presents on this particular carbon, which can result in resonance stabilization. Yeah, resonance structures, which makes this product much more stabilized than this. In this case, you can't have the resonance stabilization, so this is particularly much more unstable. But when it comes to this one, this is relatively very good. This relatively have a good stabilization, right? Because of the resonance structures. So that's the thing you need to understand. So this is a extra thing, like you need just have some small idea about this. This is all the thing you need to know about the rearrangements. So we may talk about more complex rearrangements in our later videos, and more complex structures and how they can rearrange in the or based on the orientation or ring strengths. So for now, I think this is enough, and you need to understand each of these in each of these steps, like in what situation, in what cases you can find these particular rearrangements. So I hope you got the idea.